Good morning, everybody. Just want to go over, just to remind you about the syllabus and the grades that we have in this class. So we have 4 exams, and we took one of those on, Tuesday or whatever. And that does kind of make up a big part of your grade, but then there are other big parts too. That there are the reading quizzes. And the reading quizzes count as an exam, basically. And as I said, we're going to have, I'll only count 5. And I think we had, 2 or 3 up on Moodle? We've only had 2? And we've only had 2. And you may have done poorly or not on those. I know some of you have done well. But you need to do as well as you can on those reading quizzes, because in the end, I'll add those all up, and they'll count exactly the same as an exam. As I said, I promise you 6. I'm pretty sure we'll get at least 7. And I'm really shooting for 8 quizzes. So if you've done poorly on one of those, then that means that you'll have a little leeway on those reading quizzes. But they're very, very important. I want you to get 100% on those 5 reading quizzes. You understand? It's certainly possible for you to get 100%. And hopefully you sort of gotten your stride underneath you. If you haven't done that yet, then you know what to do to get 100% coming forward. You know, a good way to read is to print out all the old reading quizzes, and as you're going through, just sort of check off the answers as you go through. Sort of look for those high points that I've asked students about in the past. In fact, I pull some questions from those old reading quizzes. I write new ones too, but I pull old questions as well. And then also, there's a project that'll come at the end of the semester, and I like for that to be a booster to your grade. It should be. It's something that you do outside of class, and it requires you to write, and I know that that's difficult for people, but you have the writing center here on campus that can help you if you have trouble with writing, and you have me to help you with the content side of that. So the project should be a boost to your grade. I'll tell you that, and then there's also the class participation. And I know that some of you are a little confused about the number and what it means. So the number that I put on Moodle is the percentage. So let's say that we've had, 10 questions over the past few weeks or whatever. We've had a lot more than that. But let's say we had 10 questions. And if you get a question wrong, then you get 1 point. I call it a point. It's not really a point. But you get 1 unit. And then if you get an answer right, you get 2 points. And then what I do in the end is I'll take whatever percentage of those that you get right. So if we have 10 questions, then there are 20 points possible, right? Because you could get each of them right, you get 2 points each. So what I say is, what if you came and you answered them all and you got all of them right? And that means that you'll get all of the class participation credit. But not all of them right. If you get all of them wrong, that means that you'll get all of the class participation. Because really, that's what it is. It's participation. It's not that you're getting everything right all the time. So that means that if you have 50% or above on that, if you had a 50 or above, then you're on track to get all the class participation. That also means that if you miss a day here, if you get your clicker or whatever, not a big deal. Just make sure that you're getting questions right, because then you're able to make up for those days that you missed. Y'all follow me on that? That's also a big part of your grade, and it counts a lot towards your grade. It's 50 points. It's like half an exam. That's your old quiz. All right? So I just tell you all that to encourage you that if you didn't do well on this exam, I know there's some of you that didn't do well, that there's still a lot of places for you to do well in the class. That even if you made a C or D, or even if you made an F on the exam, that you can still pull out with an A or B in the class. I've had students do that for many years, that they don't do well in the first exam, and then they're able to get their feet underneath them and figure out what to do. That is, if they read the book, they review the notes regularly, every day, even if it's just 15 or 20 minutes. And then they study the old exams and the old reading quizzes. Do you feel encouraged? Totally? Okay. Steven, you feel encouraged?
Yep.
Okay, good.
As far as I can. I just realized I forgot my notebook today.
Ah.
Probably sitting at my desk from when I last studied.
Probably so. It's possible to do well on these tests. I understand that especially when we get into some of the math, that you get this jumble of letters and numbers, and they just sort of swim around inside of your head, and I understand. Listen, I'm taking biblical Hebrew this semester, and I'm totally with you. Because you ever seen Hebrew characters? It looks like alien, yes, like alien letters. Sean, why don't you go? Just bring your bags in. Okay, anyway, biblical Hebrew, the letters are just like nothing you've ever seen before, and the language is completely different from what we've done. And when I look at it, I just see a bunch of squiggles and lines, but I go into it trusting that my instructor knows how to teach Hebrew, and then he knows what I need to do to learn Hebrew, and just sort of take it a little bit at a time. And that's true for y'all too. I just need to trust me that if you read the book, if you work through the old text, if you're regularly reviewing your notes, that you'll be able to get this. And then if you're just still not getting it, come see me. Then we'll dig a little deeper and figure out what the problem is. Okay? Alright. Don't think about dropping the class, of course, if you get poorly. Don't feel that discouraged, because nobody is in an irreparable position right now. We've got a lot to do to us. And drop day, in fact, isn't until the 26th. So we'll have, how many exams we have? We have another exam. So yeah, October 26th is dropping. We'll have another exam, and then we'll have a better idea of sort of how we're standing. If you do want to play around with your average, I don't report averages on Moodle because your grade is the class participation credit. It's sort of a moving target. We're all trying to get up to that 50 points. But at this point, it's not really fair to say that you have the 50 points. So that's why I don't do that. But if you want to play around with your average, I've shown you this before, but there's a grade worksheet on the website. And you can go there. It's just an Excel spreadsheet. You open it up, and you can put in your grades. All right, so you can play around. This is just some sample grades. This student made an 80, 70, 90, and 100. It's not a real student. And then they projected that they'd make a 90% on their project, but there's no reason you shouldn't make 100% on that project. If you look at the rubric and do what I ask you to do, I have no qualms giving you 100%.
Where is the rubric on here?
Yeah, it's on the website. Project rubric right there. All right? And then you can put in your class participation, and then put in your top 5 reading quizzes. Remember, they're each worth 20 points each, so all combined they count the same as an exam. And then it spits out your final average. So you can use that to play around if you're unclear about how I calculate your average. If you come to class regularly, just assume that you're going to get the full 50 points for class participation. I'm sorry, if you come to class regularly, that means that you don't miss more than 2 or 3 classes. And if you miss more than that, then it'll start going down a bit. Okay? Any questions? I'll return your exam at the end of class. In general, it was okay. I don't talk about sort of the class statistics. That's not really your business, the average and all that. But I'll certainly tell you your grade, and we saw it on Moodle. And we can sit down and talk about your exam too if you want. Either about the questions, or if you just want to, if you're still feeling discouraged, then we can come talk. I'll set you on the right path. I'll kick you in the rear and get you going in the right direction. Alrighty? Okay. Let's move on to fluid flow. Okay? It's kind of a cool topic, fluid flow. By the way, you might have noticed there were some questions. Most of the questions were new on the exam, but they were very similar to the old exams, and some of them actually I pulled from old exams. So that's a great way to study. Either as you're reading or as you're sitting in class, if you want to print some out and just sort of think about questions beforehand and bring them to class, it's a really great way to study. At some later date, I'll actually post the exam on the website, and I'll send you an email to do that. But I'll give you the answers to the questions today. All right, so fluids in motion. The study of this, that is the study of fluids in motion, is called fluid dynamics. Your book defines it. Oh goodness, oh by the way, let's do a quiz, reading quiz. I guess on Tuesday, huh? We'll do a reading quiz on the second part of this chapter. That is, somebody see their book? Or your book?
Is that the applications?
Yeah, the applications, I think it's page 48 on. Yeah, page 48 on. So we'll do a quiz on Tuesday, reading quiz. Remember, I'm going to throw these things at you as 48 to 68. Chapter 2, reading quiz. I'm going to throw quizzes at you as much as I possibly can. It's great for you. It helps you to keep on track. And as I said, the more quizzes I get, that means the more I get to drop. All right, anyway, so the study of this is called fluid dynamics. Fluids include not just liquids. It's not just a liquid that's a fluid, but a gas is also a fluid. It includes all things that can flow. Right, that's where the flu part of fluid comes from. The same root as flow. And so that includes liquids and gases. Well, there are actually some solids that can flow. Have you ever heard of the pitch drop experiment? No? It's kind of cool. I'm not going to show you. But pitch is comes from trees, I think. They used to use it on boats. They would heat it up and put it on boats to seal them up. But it's really hard. Like, you look at it, you can crack it with a hammer, and it's black. It's just sort of really hard. But the pitch drop experiment, you'll Google it, is an experiment to see the flow of pitch. They take this really hard chunk of pitch, it's like tar sort of, and they put it in a glass container and they leave it. And then years pass. Years and years and years. But eventually that pitch conforms to the container, and then it slowly, after many, many years, will drop, like produce a little drop that will fall to it. It flows like a fluid. Isn't that cool? It's called the pitch drop experiment. You'll take a look at it. It's pitch drop. All right. So we have three characteristics of fluid flow. It can be steady or unsteady. And to be steady, which is going to be a characteristic of ideal fluid flow, which is what we'll deal with. Steady means that the velocity at a point does not change. So if I have a fluid flowing through a pipe, what this says is that at this point, the velocity is constant. That if the velocity at this point is 2 meters per second, then it's always going to be that. Actually, we'll measure the velocity in a different way. We'll measure it in a cubic meter per second, a volume flow rate. So if we have a certain amount of fluid flowing here in a certain period of time, then that's always going to be the same. Hey, Sarah. Rotational or irrotational. The property of an ideal fluid is that it's irrotational. Yeah, Kate? When we're looking at ideal fluid flow, we'll look only at steady state fluid flow. That means that the velocity is always constant at a particular point. Yes. Unsteady is going to be non-ideal, and that's sort of beyond this class. Unsteady, by the way, the velocity here could change. At this point, it could be 2 cubic meters per second at one time, and then 5 cubic meters per second at another time. Because you just have more stuff turning around inside the fluid. Rotational or irrotational? Irrotational means that it doesn't rotate. So we have fluid that will flow in a straight line like that, as opposed to a fluid that flows like that. So, like for example, in your water hose, when water flows through your water hose, that's pretty much irrotational. It's always going in a straight line. Can anybody think of a rotational flow of fluid?
Whirlpool?
A whirlpool? Yeah, I was thinking of a more common thing.
Tornado?
No, not
Hurricane?
Yeah, hurricane. The toilet, right? That's a rotational fluid flow, isn't it? Yeah, it rotates. So anytime, all those things are rotational.
But it doesn't continue to do that through the pipe.
No, once it goes into the pipe, then it becomes like irrotational. It doesn't rotate. viscous or non-viscous. For ideal fluid flow, we're going to be looking at non-viscous. And viscosity describes the friction between molecules. It's sort of how sticky is the material. If you have a material that's really sticky, that means that the molecules stick together, right? Like maple syrup, for example. It's a viscous thing, right? And it's really because the molecules, they stick together, and they don't move as well. That's why it moves more slowly. You know, maple syrup, pancake syrup, oil, it's fairly viscous, really thick oil. So we'll deal with non-viscous, things like water, for example. And then compressible or incompressible. This is where we're going to step not into the flow of fluids, but into the flow of liquids in particular. Because we'll look at incompressible. And so that means that we'll deal only with liquids. Remember, fluids include both liquids and gases. And what incompressible means, we've seen this before, but when you apply a pressure, the volume remains the same. And then finally, laminar versus turbulent. Laminar means that the fluid flows in parallel layers with no interaction between the layers. So we'll think about fluids, as I said, that they will flow sort of with these steady streams, all in one direction. And that those, if we imagine our fluid being broken into these different layers, the layers will not interact with one another. They'll maintain a relative position that's the same. The layers near to the sides of the pipe will move more slowly, however. And usually this occurs, this moving more slowly, does it occur for viscous or non-viscous materials? It'd be viscous, right? Because if I have, imagine my pipe right here, what we're saying is that over here it moves more slowly. And why would it move more slowly? Why would the fluid move more slowly at the sides? It sticks to it, right? And so viscous materials will stick to the sides. So this usually occurs for viscous fluids. And what do you think? Is it going to occur at low or high speeds? Will you get that slowing down at a low or a high speed? Will it stick at a low or a high speed? At low speeds. At low speeds. Yeah, so usually this occurs for viscous fluids at low speeds. Most blood flow is laminar. That's why it's relevant here. We'll talk about how blood flows, except for in the heart. Not laminar blood flow in the heart. It's a very turbulent blood flow in the heart because you're moving it and pumping it out into the circulatory system. Turbulent, these layers interact unpredictably. The velocity of the fluid changes. I think it changes a lot. And sometimes blood flow is turbulent. Not laminar, but turbulent, such as in the heart, when it contracts. And when that happens, blood rushes quickly into another chamber. And when you get that, you get there's different layers are all mixed up. And you also get rotational behavior where the fluid rotates in these swirls and eddies. This causes a distinctive sound. You might have heard, like, when you listen to a person's heart, y'all ever listen to a heart? When it contracts, it makes a very distinctive sound, and it's because of that turbulence. All right. Let's try a couple of these clicker questions. We'll do the one on the left here. Which of these is not a characteristic of ideal fluid flow? Yeah, sometimes. I usually try to record every class. And so if you go back and look at last year's class.
Okay.
Why?
I'm just trying to keep up with typing.
Okay, yeah, and I'm recording today's class too.
Okay.
I'll try to record it every day. All right, let's stop at 45. But if you need me to slow down, by all means.
I don't want to hold up the class.
No. Is he going to hold us up? No. Like, if people care, they're certainly welcome to slow down a bit. All right, he is right that all of these are characteristic. I see some of you put that laminar flow we'll consider to be an ideal fluid flow. All right, I know that, like, as we get this slowing down on the sides, like, that doesn't really seem like ideal fluid flow, but we'll consider it to be ideal fluid flow. So all of these are characteristic of ideal fluid flow. All right, liquids are what and gases are what? All right, let's stop at 12, 13. Oh, C is right. Liquids are incompressible. They don't get smaller when you apply a pressure. That's what allows us to use hydraulic systems. That's why Pascal's principle is true, because liquids are incompressible and gases are compressible. And that's what we define by the ideal gas law. That whole PV equals nRT, it describes when you apply a pressure what happens to the volume. Remember we saw that with the lungs. And the PV is constant, that when pressure increases, volume decreases, and vice versa. And that's part of the ideal gas law, but it was a special subset. Do you remember the name of it? There's a person's name. Boyle's law, right. And that describes how our lungs work. That when we breathe in, we're making our chest cavity bigger, V goes up, P goes down, air rushes into our lungs, and when we breathe out, we make the chest cavity smaller, V goes up, V goes down, P goes up. And so that forces that high pressure air out of our lungs. Boyle's law at work in our lungs. We'll see it again in the iron lung. There's another way of Boyle's law working. All right, so liquids are compressible, or incompressible rather. Gases are compressible. And what do you call cheese that doesn't belong to you?
Nacho cheese.
Have I told that one?
It's just very common.
It's just.
It was on a commercial.
I thought I made it up. Yeah.
The next one, can I do a
I don't know. I don't know.
Can I show you a joke?
Is it vulgar?
No, it's about physical science.
Okay. Yes, you can have the floor just when we have another question. All right. Flow rate is interesting.
Yeah, but she said it was interesting. What I said was interesting.
What about the joke?
I just found something really funny about physical science online.
She's an interesting person. All right, so flow rate. When we talk about a rate, anytime we talk about a rate, we mean how something changes with time. right? So like velocity is a rate. How does position change with time? Acceleration is a rate. How does velocity change with time? We'll see later that momentum, when we get to momentum, that it's a rate too. How does force change with time? Or rather, I'm sorry, that force is a rate. How does momentum change with time? We'll see that. We'll get to that. But right now we're talking about flow rate, and this refers to how a volume or how a flow of fluid changes with time. And we'll define it in this way, that Q is equal to volume divided by time. And so the SI unit for this, the unit is going to be cubic meters per second. And it literally means, like, if I have a cubic meter of a liquid, how quickly does it move through space? And if I sit at a given point and I measure all the liquid that's moving past that point, that is my flow rate. How many cubic meters are moving past this point in a given amount of time? Okay? So in a pipe, the flow rate must be the same in different parts of the pipe. It's based on the assumption that fluids are neither entering nor leaving the system. And it's also based on this idea of the conservation of matter. Which says that, you've probably heard this before, we have some big conservation laws in science, and conservation of matter is one. We'll see some others. Conservation of charge is another. Conservation of energy is another. But in the conservation of matter, it says, in a closed system, matter is constant. The amount of matter that you have is constant. This is pretty much a closed system. In this room, I mean, we have some air that's coming and going, but for the most part, it's a closed system. The entire amount of mass in this system is not changing. We have the same amount of stuff, right? It's a closed system. And so that's the conservation of matter, that the amount of matter in this room is constant. And that's true for fluids too. It says that if I have a pipe and I have a certain amount of fluid right here that's traveling at a certain speed in that direction, I have a certain flow rate, then I have to have that same amount of fluid over here that's still traveling with the same flow rate. Now what gets tricky is when my pipe gets smaller. And so then what's going to happen to my flow rate? If my pipe gets smaller, how do I maintain the same flow rate? Because if I have 3 cubic meters per second going through this pipe, I still got to have 3 cubic meters per second going through this pipe. Because otherwise, I'm losing fluid somewhere. So, well, let's not talk about the pressure right now. You're right. But what happens to the flow rate? No, the flow rate has to stay the same. That's the thing. Like the flow rate, this volume per unit time, has to stay the same. But what happens when the volume of your pipe gets smaller? What happens to that fluid? How do you get the same amount of fluid going through the pipe? How do you get the same flow rate if the pipe gets smaller? No, not pressure. Pressure is involved. Something's got to increase, right? What's going to increase? The speed. That's right, Sarah. It's going to go faster, right? The volume gets smaller, but it goes at a faster rate. And so I keep the same flow rate. So the flow rate equation says that Q1 is equal to Q2. Remember, Q, that's what we're using for flow rate. It's the variable that we use for flow rate. So Q1 is equal to Q2, where Q1 is the flow rate here, and Q2 is the flow rate here. But we can express flow rate in this way. We can say that, well, flow rate, we've already said, I'll write it over here, that Q is equal to volume divided by time. Let me break it down just a little bit. Volume is equal to an area times a distance. Just in general. Like say that I have a cube here. All right, let's do a cylinder actually. Let's not do a cube. Let's say that I have a cylinder like that. The top of this cylinder has a certain area. And then the cylinder also has a certain height or distance. And so if I wanted to find the volume of this cylinder, all I do is I would calculate the area of the top of it and then multiply that by the distance, just in general. That's true for cubes too, right? That I calculate the area of one face of the cube and then I multiply that by the height of the cube, and that gives me the volume. So the reason I say that is that if I do area times distance divided by time, then we see something here that we've seen before, and that is this. What does distance over time give us? It gives us our speed, right? So Q can be generalized, or I guess made more specific, as area times velocity. And that's what the flow rate equation does, is it says that my Q1 has to equal Q2, but then further, A1 V1 equals A2 V2. And that's pretty powerful because what that says is that if A goes down, as it does here, that V goes up. Because each one of these remains constant, like this value has to always equal this value. If I have 10 over here, I also have to have 10 over here. And so if this value decreases, that means that this value has to increase. Okay?
Is the acceleration or the area?
A is the area. I'll use lowercase a for acceleration and capital A for area. Stephen?
Wait, how did you get time on the area?
Oh, right here?
Resistance? Yeah.
Okay, so time is our definition of flow rate.
Uh-huh.
We define flow rate as volume over time.
Uh-huh.
And so this time is carried over. But then I broke down volume to be area times distance, right? Cylinder, find the area of the top part, and then multiply it times the height, and that gives me volume. And then it's sort of a dimensional analysis, hand-wavy type thing, where I say, oh, distance over time, that's my speed. That's how I define speed.
Okay. And then the time just and distance just cancel out?
No, they don't cancel out, but they become the speed. No, distance over time is the speed of the fluid.
Okay.
Good question. They're all good questions. I'll never ask a hard question. Okay. I guess, unless you guys, can I go? No, that's a good question. I'm excited for it. I'm looking forward to it. So, you ever try to spark somebody with a water hose? What do? You put your finger over the end of it? Unless you have a nozzle, but let's imagine you don't have a nozzle. Put your finger over the end of it. What does that do to the water coming out of it? It doesn't just spread it. I mean, it does spread some. But more important, yes, all of you are saying the right thing. That when you put your thumb over the end of a hose, that decreases the area, right? If I decrease the area, that means that the speed must increase. So next time you squirt somebody with a water hose, say, oh, it's the flow rate equation.
So isn't that what a nozzle is doing?
Mm-hmm. Yeah, when you have a nozzle, that's what it does it, but it does it better than your thumb. Alrighty? This is called the equation of continuity, by the way. I'm not sure that your book calls it that, but if you just want to impress your friends, does your book call it that? Do y'all remember? Yeah. This is in your book, though, right? Oh, come on, it's there. We have a quiz on Tuesday. Listen, the way to do well is every day. I know this isn't normal for students. It's not normal for me. You got to force yourself to do it. Every day, spend 20 minutes reading through the book, studying the old test, reviewing the notes. Every single day. And you know what? If you did poorly on the first exam, maybe more than 20 minutes. But if you made a B or an A, probably 20 minutes every day is enough. If you made less than that, maybe 45 minutes to an hour a day. I know y'all have an hour every day. Right? Y'all have an hour? Just take your Netflix time and maybe don't do that for an hour or whatever. I know that y'all work hard and you have other classes. But what?
My calculus homework takes me like 4 million hours.
4 million?
And it takes me
Yeah, are you at 165?
I don't know. No, I think it's just 160
Oh, okay. Is it?
for business.
Oh, it's business calculus. Okay. Alrighty. Let's see. Let's do an example. So a pipe has a cross-sectional area of 20 centimeters squared. The water flows through the pipe at a speed of 30 meters per second, and then it gets smaller to an area of 10 centimeters squared. What is the speed the water now traveling? Y'all work this. I'm going to give you some options, and we'll do it as a clicker question. How about that? Let's see here. I always like to draw a picture. I'm going to draw you a little picture here. This is what your pipe is doing. It's going from 20 centimeters squared to 10 centimeters squared. Picture always helps me to think about the problem. And these are the options that you'll have. Oh, you're amazing.
I know if you would have my chemistry class the other day, because I forgot my chemistry. And so check bring it up, but this is not
Oh, I'm sorry. With what speed is the water now traveling? Okay, so we're doing the second question.
I was confused.
Yeah, sorry about that.
Wait, doing what? The second question.
There are two
Says,
questions.
with what speed is the water now traveling?
We'll come back and answer the first question, Dorothy. But this is the one we're doing now. All right. We're a little bit split on the right answer, so why don't y'all ask around what your neighbors put. Say, hey, what'd you put? Okay? Ask yourself, does it speed up or slow down going into the smaller pipe? That'll help you get rid of some answers. Or does it stay the same? You folks talking to one another back there? Blade? Tristan, right? Yeah. Trisha? Caitlin? What did Blade put? You don't know. Ask him what he put, okay? All right, we'll do this a few more seconds. We'll stop at 2:12. 2:12. This might be your moment to shine, Tyler. We'll see. Oh, that's close enough. All right, so C is right. It's 60. As I said, think about first. Does this thing slow down or speed up? Well, I'm putting my finger right over the end of the hose to make the area smaller, so it's got to speed up because I'm going to have a big area here, so I have a small velocity. So that means I have to have a big velocity here. And this is all borne out in the continuity equation. A1V1 is equal to A2V2. Oh, so I know it gets bigger. That means that these two answers go away, A and B. Before, y'all were split between A and C. But because the pipe gets smaller, you can rule out A. The fluid can't be going the same speed. It certainly can't be going slower. And then, it could be C or D. Let's see. Although you could say, well, look, my area went from 20 to 10. My area was cut by 2. That means my speed is going to be increased by 2. Oh my. That's so easy, is that what you said? That's exactly what I did. But if you don't want to do that, it increases by 2, it goes from 30 to 60. We can just do the math, right? I mean, you did the math in your head there, but we can write it out. So A1 is 20 centimeters squared. V1 is 30. I guess you could. I don't know what the butterfly is. All right, and then that's equal to A2. Let me just show you here. 10 centimeters squared times V2. I'm looking for V2. And then if I want to solve for V2, I'm going to divide both sides by 10. So that cancels out. And that just leaves me V2.
That's super complicated.
That's not complicated.
It's not like basic algebra.
I don't know proportions how you do it because I didn't come up with it.
Yeah, I'm not sure how you do it with proportions. I mean, you just take this and rewrite it a little bit, I guess. That A1 to A2, A1 over A2 should equal V2 over V1. But that seems more complicated. Okay.
Oh yeah, that's wrong.
Good. But I want you to not really have to think about the equation. I mean, think about the equations, but think about how, if one variable changes, how does that affect the other variable? But if you have to write it out like this, that's fine. All right, and so that's 600 divided by 10, which is 60. So V2 is equal to 60. Again, I understand. It's been a long time since some of you have used algebra, but this is sort of the topmost level of algebra that we'll use. Okay? C is right. Oh, did you tell your joke? Go ahead. Yeah, this is getting complicated. Is it going to take a long time?
Worth it. No. You trust me?
Yeah, go ahead.
If this is good, you could steal it.
Okay. He slaps the car?
Yeah. Isaac Newton slaps the car. The car slaps Isaac Newton.
It's Newton's third law.
Huh?
Yeah.
Yeah.
Yeah. That's the third one.
All right. My level of reflection just rose a couple of notches. Let's see.
Was it worth it?
It was.
Yeah.
All right. So viscosity describes how thick a fluid is. Different materials have different viscosities. Certain things affect viscosity. Temperature affects viscosity. Right. Usually, cold is more viscous. Although not always. Actually, let's watch a video.
So what happens to organic matter lower down to such temperatures?
I mean, it would freeze, of course, right? I don't know. But the point here is that it loses all viscosity, and that's what allows it to just move through that barrier. It's like going to McDonald's or wherever and asking for a cup of superfluid helium, and they'd give it to you, and you'd hold it, and it would just all fall out the bottom of the cup. It's like, man, you pay a lot of money for this superfluid helium, and then it all pours out the bottom of the cup. There's no viscosity. It just moves past the material like it's not even there.
So is it the liquid helium that he was, but he wasn't using a glove, he was just using a little teacup for it in there. Is it not cold already?
Yeah, it's really cold.
Oh,
Right? Like, helium in it.
pouring it in there. In the beginning of the video.
Oh, I'm not sure what that is. Huh? Helium? Is it flammable? Anyway.
Is it just helium or is it other elements too?
Yeah, I mean, other elements have a really cold liquid state, like helium.
It's just in general, so at absolute zero, things will be able to fluidly move through objects.
Oh, I don't know about that. I'm not sure. Yeah.
So, what is a superfluid?
A superfluid? Well, a superfluid, I think, is by definition that this viscosity is zero. It occurs at very low temperatures. Yeah. All right.
Okay, so how do they know what happens in absolute zero if they can't reach it? It's just a theory?
It's a theoretical state. What he was saying is, we'll get into this in a later chapter, is that you can't reach that state because in order to reach a lower temperature, you have to have some other object that is a lower temperature than the temperature you want to get to. Like if you want to get to 5 Kelvin, then you need something that's 4 Kelvin to draw it down to that lower temperature. You understand what I'm saying?
Yeah.
Or they leave it in Antarctica and then watch it for like 5 minutes. It would just become as
It's
cold
not
as
that
the
cold.
surface.
Right, it would just get as cold as its surroundings. But when we get into thermal physics, we'll talk about that.
I'm gonna get into thermal physics.
Mm-hmm. I know, it's a crazy class. All right, so the viscosity affects the flow rate. Viscous fluids like blood, they need a constant pressure to make them flow. But non-viscous fluids do not need a pressure. I mean, if you have a viscous fluid, it takes a constant pressure in order to keep it going. But if I have a non-viscous fluid, it's like no friction. It's just going to keep going. Like Newton's first law, it'll just keep going forever and ever. Right, but blood is a viscous fluid, so you always have to have this constant pressure. That's why our heart, boom, boom, that's why it always has to be pumping. Superfluids have no viscosity and will move through barriers with no resistance. What's that? the fluid when you process food, is it viscous? Yeah. Sure. Sarah?
So if superfluids are able to move through barriers, how are they able to contain
That's a good question.
I don't know, Sarah. I don't know much about superfluid. I just thought it was a cool video. But when they had it before, when it was down inside the container, it's like the liquid helium could sort of move in and out of the little bitty glass that was inside. So you had all the liquid helium, and then you had the little container inside the liquid helium, and because it was in the superfluid state, it could move in and out of the little container that was inside the bigger container. But then when they pulled the little container up, then it allowed that helium, the liquid helium, to escape from the little
well,
container.
that's how you have to escape from the container.
Oh, I don't know.
It might be the liquid that was inside the container holding it.
Yeah, I'm not sure.
This could
I
be
think it's
something
when
right
you're
here.
inside the container, just screw it.
It was, yeah, it was just super cool.
Can we have him as a guest speaker?
I guess so. I'll look him up.
Guest speaker.
All right. There's no viscosity between the atoms of the superfluid and the atoms of the barrier. They just go right past one another, like they weren't even there. Is it about superfluid?
Yes.
Oh, for goodness sake.
Never gonna show that video.
So like if you reached out your hand, right, and you had some of that fluid stuff, superfluid stuff in your hand.
If it maintained in a superfluid, it would just go right through your hand.
It'd probably kill out all the cells in the
Yeah, you would die and all that, but what?
You know those okay, what is it called? It's an atom that when you see it, you can't see it, and when you see
Mm-hmm.
is that like a superfluid?
Sort of like that, right. So it gets down to quantum mechanics, and in quantum mechanics, there's this idea that you don't know the position or the velocity exactly right at any one time, that you can know the position, but you can't know the velocity. And it allows for us to have things like tunneling, where objects, materials will move from one place to another through a barrier. So yeah.
Wormholes? Wormholes?
No, it's different from wormholes.
Yeah, I learned that in chemistry, and that's more on those much stuff.
Yeah, it's a cool thing.
So wait, can water be a superfluid?
No,
No?
no.
Because it can't get that cold.
Because it would be a solid when it gets that cold.
If water was a superfluid, every single time you drink, you drink. Every single time you drink, you drink.
Let's do this question, please, and then I'll hand back the test. All right? We'll do these two questions. What are the units of Q? The flow rate has which of these units? If you finish that one, go on to the next one on the right. All right, let's stop at 33. Very good. A is right. It's cubic meters per second. You'll see some questions like that on the test, just sort of basic identification stuff. Let's try this one over here, too. Doing pretty well. A couple of you don't have the right answer, so ask around, ask your neighbors. There are two more questions on the next page. All right, so let's stop at 22.
In the example that we did earlier, we didn't answer the first question. I just want to know if I did it right.
Oh yeah, I'll go back to it. Let's finish these. I'll go back to it. Here the answer is C. That if my pipe, this is just like the one we did earlier actually, but just with letters instead of numbers. The pipe gets smaller by a factor of 2. That means that here I have a small V and here I have a big V by the same amount.
How do I get it right with this one, except when the numbers came from that one?
I don't know, Kate. We can take a look at it, and I'll see. Maybe you just did your math wrong. But if my area, if A2 gets small by a factor of 2, that means that this has to get big by a factor of 2. If this is halved, that means this has to be multiplied by 2. All right? Hey, what do you call a boomerang that doesn't work? A stick. All right, two more on the next page. Oh, well, let's go back. This one, the flow rate here, the flow rate is this, right? This is Q1. And so Q1 is equal to 20 times 30, and that's equal to 600 cubic centimeters per second. So that is the answer to this question.
You don't have to like put it, because I know the original units was meters per second. So
Oh,
that's why, or whatever.
No, I won't make you do that. All right. You won't see many unit conversions. I don't think you'll see any actually here on out. Let's try the one on the left here, and then the one on the right. $8.50 we get out of here, is that right?
Yes.
That's right.
I thought it was like 8:15.
It's not 8.50.
So we can pay 40.
Oh, y'all don't know. You don't know. I've been working here 13 years. I know when the class is. All right, we'll stop at 30 seconds. 30. Turbulent is right. The type of fluid flow that causes that sound is turbulent flow. No, laminar is when it's just moving straight, everything's all in order, but turbulence where it's all topsy-turvy. And when your heart contracts, it makes this distinctive sound. I forget what it's called. What's the sound? Y'all know? All right. Let's try this one on the right. Which of these is not a characteristic of ideal fluid? Are we reading this one already?
Yeah.
All right, we'll go ahead and put in the answer. Answer is E, by the way. We did it before. You got it right? All right. 43. I'll stop. E is right. Hey, what's the name of a lady with one leg?
Peggy.
Eileen.
Oh, God.
And I like that joke. It's a funny joke. But I fear that one day I'll have a lady with one leg, and like it's kind of a mean joke if I had a student with one leg, isn't it?
I don't know.
Huh?
It doesn't sound.
If you had one leg? What was I saying? Oh,
You should do that when we cover the balance and all that.
oh yeah? Mm-hmm. Okay. I want to give back your exams because I also want you to have some time to mark down the right answers. But hold on. Give me just a minute. Annette, you want to come on?